Okie dokie, let's see. How can you estimate the area under the curve? So our objective, you'll find basic sums to use sigma notation and use properties of sums. So we'll look at those properties toward the end. But the first thing we want to explore is how we can estimate the area under the curve. So the area under the curve is going to be all of this. But obviously, that being curvy, we need different shapes. So maybe one way would be to make a triangle. Maybe another way would be to make a rectangle and a rectangle. Or maybe you're like, wait, that's too big. So maybe I say I'm okay with that first rectangle, but then I want some sort of smaller rectangle. There are a lot of different options. I'll let you think about what might happen there. Suppose we could go for a circle too. All right, so let's try to actually do it. And I'm going to, let's do it by some shapes. Maybe I'll do this shape and this shape and this shape and this shape. I don't know, something like that. So I'm going to have a triangle that's 1 by 1.5 divided by 2. And I actually have two of those, right? Because I have one on the other end. So that checks off those two triangles. And then I'm going to have a rectangle that's 1 by 2. And then I'm going to have a rectangle that is 1 by 1.5. So when I add that up, those will cancel. So that's 1 1/2 and 1/2 is 3, and 2 more is 5. So I got an answer of 5. All right, now let's see. If we just think about this, well, I'm going to color on it. So I suppose I could do, I don't know, some sort of triangle. And triangles are more difficult because that'll turn like trapezoidal, so that makes me a little bit nervous. So maybe I'll just make a rectangle, something like this. So just make triangles on the end and then some rectangles. But I see that I have more pieces there. So the thing I should be keeping in mind is, what's the advantage of having these more pieces? What does that do for me? Versus the previous one where I only had, what was it, 4 pieces? Now I have double that. So what's the advantage of that? What is true about my estimate here? Okay, how can I write the sum idea more succinctly? Well, we may or may not have talked about these in previous classes, but I bet it has to do with an idea of a sigma. So a sigma means adding things up. So we're going to have to figure out how to add all these pieces up. It would be helpful if we had like a uniform way of writing it, but I'm not going to go there yet. But I bet it's going to involve that sigma idea. Now let's see what we got. It says sum definitions theorem. Take a look at these. Which of the pieces of information is familiar in terms of content we've already studied? Okay, so sigma notation. So I just mentioned that. AK is a function of k. M and n are non-negative integers. M is less than or equal to n. Then, so they're saying if I have the summation from k equals m to n of ak, that's like am plus 1, etc., up to an. That's a little confusing. So let's put it in actual context. So suppose I have the summation from k equals 1 to 5 of k squared. So that's going to be, I'm pausing because I want to give you some notation here. That's like your AK. So that's A1, A2, A3, A4, and A5. In this case, A1 is we're plugging in 1 for k, so that's 1 squared. A2, plugging in 2 for k, and 3, and 4, and 5. So that would be how we would write that down. So the summation notation, or the sigma notation that we have over here, that's just a shorter way of writing these big long sums. Now I only have 5 terms there, but you could have lots and lots and lots and lots and lots of terms. So I'm using the word terms. Each of these is a term. It's based on this, which is your general term. Now let's see what we got below. Constant, multiple, and sum rules. So if a, k, and b, k are functions, and c is any real number, then if we add up CAK, that's the same thing as adding up AK and then multiplying by C. Okay, that's familiar to me. Because that's familiar, if I want to take the derivative of 5x squared, that's the same thing as saying take the 5 out, take the derivative of x squared, so it's 5 times 2x. Or, similarly, if I want to take the limit as x goes to 3 of 5x squared, that's the same thing as saying take the 5 out, do the limit as x goes to 3 of x squared, and you'll get the same answer. And then for part B, if I sum up as a sum, then that's the same as the sum of the sums. That's confusing, huh? So that's familiar also. If I take the derivative of sine x plus x squared, that's the same thing as saying, let's just take the derivative of sine x and then add to that the derivative of x squared. It's also the same if we think of limits as saying if we got the limit as x goes to 2 of 5x plus 3x squared, well, I could just think of that as the limit as x goes to 2 of 5x plus the limit as x goes to 2 of 3x squared. We did things like that when we were proving derivative rules, where we broke limits into pieces to separate off pieces that would cancel out and that sort of thing. And then that last part there says, given any function and any integers from m to n is the same as going m to somewhere and then p to somewhere. Okay, so let's give an example of that. So my example of that is going to be, if I'm adding, I'm going to go back to that one I already had. From k equals 1 to, still make it 5 of k squared. That's the same thing as saying, add up from k equals 1 to 2 of k squared, and then do from k equals 3 to 5 of k squared. So the first one's going to be 1 squared plus 2 squared. And then the second one's going to be the 3 squared plus 4 squared plus 5 squared. And that works out to be the same thing we had before. So that's just saying we can break the sum wherever we want. Okay, this is doable. So now this gets to what we're going to do. And we're going to do an activity to help you figure these pieces out. So the objective is still, we're going to find Riemann sums to estimate the area under the curve, also known as rectangular sum, some of these. Your first job is to do the Riemann sum intro, so we're going to have that, and then we're going to fill in these definitions. So we're going to be able to define a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, and a trapezoidal Riemann sum, or a trapezoidal approximation is what it's also often called, trapezoidal approximation. And sometimes these left, right, and midpoint things are called left rectangular approximation method, or RAM. But we will talk about that, and you will play with that.